Welcome to statics. In this case, we want to draw the shear and moment diagram for a cantilevered beam. And anytime you see the word cantilevered, you must automatically, at this point, be able to realize that there is an inherent moment that comes along with a cantilevered beam. That is to say, that there is a reaction moment at the wall as a result of this entire beam sticking into the wall, basically being cemented into the wall. So in addition to there being a possible AY and a possible AX, there is also a moment because it is a cantilevered beam. So this is my free body diagram over here, and step one is always, as before, we got to find the external reactions. So let's, and I'm working on this diagram over here, so let's begin by summing the forces in the y direction and setting them equal to 0. And we see that AY minus 10 minus 40 is 0 because the beam is in equilibrium, and therefore AY is equal to 50 kilonewtons. Similarly, when we sum the moment of the beam, and let's imagine that we're at the point A, the beam is in equilibrium, and therefore this reaction moment must be included. I've drawn it as positive, so I'm going to write positive MA, and then I have a negative moment occurring from the 10 kilonewton force and the 40 kilonewton force, so I have minus 10 times 5 meters, and then I have another minus 40 times 10 meters. And therefore, MA is equal to 450 Newton meters. And so I can clean up this diagram a little bit by, and then also AX is 0. So I'm just going to clean up some of these values so that I have a kind of more coherent diagram. So AX is 0. I'm not going to redraw it. And what I've just concluded is that AY was 50 and that we had a reaction moment here of 450 Newton meters. Okay, so that's step one. Step one is always find the external reactions. So let's step away from it for a second and see if our answers make sense. Yes, it makes sense that 50 is equal to 10 plus 40. It makes sense that that the moment is going to be in that direction. So we're ready to move on to step two. All right. Step two involves breaking the beam up into similar regions. So I'm going to call this region 1. I'm going to call this region 2, and then this will be my last region out here. And we're going to just take this beam apart, cut by cut, and draw the free body diagrams. So my first cut is going to be there. That's going to be cut 1. My second cut will be here. That'll be cut 2. And then my last cut will be somewhere in the middle of this beam out there at cut 3. All right, so let's cut it up. Here we go. So first region is 0 less than x is less than 5. We're in region 1. Here's my tiny chunk of a beam. It's the left-hand side of the beam, so I draw shear pointing down, and moment looks like that. I worked out that that was a 50 kilonewton force, and this time, since there is a reaction moment, I've got to include that in my diagram, so that's what's different about this problem. And we proceed, we sum the forces in the y direction, set them equal to 0. We find that minus shear plus 50 is 0, and therefore shear is equal to 50 kilonewtons in this region of the beam. Similarly, we can sum the moments at the point of cutting. So that is to say, I'm thinking about being at this position, and now I'm summing the moments and setting them equal to 0. So my unknown m must be included, so I write m. I write it as positive because it is counterclockwise as I've drawn it, which is the convention of drawing it for the left-hand side of the beam. I must add this bending moment, so it is positive as well, so I write down 450 for that. And now I have to think about the moment caused by this 50 kilonewton reaction force occurring at A. And so we must define a distance. So let x be the distance from the origin to the cut. So this 50 Newton force is x away. It's going to be creating a negative moment, so I write negative 50x. And therefore, moment is equal to 50x minus 450. So let's check, is dm dx equal to shear? So if I take the derivative with respect to x of this equation, I will get 50. 50 matches this value here, so things look pretty good. All right, so what this is telling us is that we have on our shear and moment diagrams, we have value for shear, which is just simply a flat line at a magnitude of 50. So let's make that equal to 50, and we have a flat line. It's between 0 and x and 5, and the moment at x equals 0 is equal to negative 450. When x is equal to 5, it will rise to be what looks like 200. So it's going to be doing something like that, where that is 450 and this is 200. And I'm just doing these roughly here. All right, we're ready for region 2. All right, region 2 of the beam means I'm cutting it right here. And we have a choice. We can look at the left-hand piece or we can look at the right-hand piece. Either way, we'll get the same answer, we hope. So let's just continue to draw a left-hand chunk of the beam. And so we still have the 50 kilonewton reaction here. We must include the 450 kilonewton meter moment. We've cut it, so we have to include that shear and that bending moment. And now look carefully back at the beam to make sure to pick up the things that happen along the beam that we need to include. And so we must include, this time we have to include the 10 kilonewton load at 5. So let's add that in here. So let's imagine that this position here is 5 and that's 10 kilonewtons. X is defined as being the length to the cut. The length to the 10 kilonewton force is 5 meters, and I'm doing this because I need to know this distance right here. And that distance right there, if that is going to be just x minus 5. All right, so we know what to do. We're going to write our equations of equilibrium. We're going to sum the forces in the y direction, set them equal to 0. And so we get minus shear minus 10 plus 50 is 0. Therefore, shear is equal to 50 minus 10, which is 40 kilonewtons. Okay, so let's have a look at our diagram and see how that looks on the plot. So what we've just found is that in this next region of the beam, we dropped by 10 and we're have a constant value going over there at 40. It makes sense to us that it dropped by 10 because it experienced a 10 kilonewton load there. And so now let's consider what's happening with moment. So let's go back to our cut, and I should always label what you're doing so your poor professor can follow what's going on here. So I'm cutting between 5, which is less than x, which is less than 10. That's my second cut, and that's what I'm doing now. All right, so we look at the equations of equilibrium. We're going to sum the moments at the point of the cut, that is to say right there. So what do I get? I have to include that. That's what I'm trying to find. I'm going to get a positive moment from this 10 kilonewton force. So I write 10 That's the load. I need the distance. We decided the distance was x minus 5. So that takes care of that. I have to include the 450 again. That's positive. And I have to include this 50. And that's negative. 50. What's the distance between that point and the cut? It's just x. So if we simplify that, what we see is that m, and that's of course all equal to 0. M is therefore equal to 50x minus 450 minus 10 times x minus 5. It's sometimes tempting to expand all this out and solve it, and your calculator can do that for you, I guess, but it's actually kind of easier sometimes to leave it together. So for example, if we plug in x equals 5, we can see that this term is going to go away, and we're just going to be left with 50x minus 50, which was what we had here, right? And that's kind of a comforting fact, because it's when a good checkpoint is to make sure that the moment pieces, as you start the next piece of the beam, have a correspondingly similar value, unless of course there's a couple or something applied at that particular point. All right, so let's do our second check, which is to check dm dx. So dm dx, I see that I get 50x minus 10x, that's 40x. Sorry, there's no x left because it's the derivative. It's 50 minus 10, which is 40, and that matches what we got before, so life is good. So that's a check. Always do this check. It will help you find a mistake in one place or the other. All right, so let's plot what's going on there. If we already figured it out that it was 450, what happens when we plug in x equals 10? When you plug in x equals 10 to this equation, you get 0. So we end up over here on this curve doing something like so at x equals 10, we wind up at about 0. I'm not sure I have the slope correctly here, but you can do that a little more carefully at home. All right, so let's go to region 3 of the beam. All right, so why don't you see if you can do this on your own and hit pause, and you do region 3 and then come back. So for region 3, we have a choice of two things. We can look at the left-hand side of the beam, or we can look at the right-hand side of the beam. If we look at the left-hand side of the beam, shear is down, moment goes like that. On the right-hand side of the beam, shear will be up and moment will be like that. On the left-hand side of the beam, I've got the reaction load of 50, and I've got the bending moment of 450. On the right-hand side of the beam, I've got nothing. So this side of the beam looks a little easier to analyze, and so that's what I would like to do. So when we sum the forces in the y direction and set them equal to 0, we see that shear is equal to 0. And when we sum the moment at the cut and set that equal to 0, we see that minus m is equal to 0. So therefore, shear and moments are both 0 for this last part of the curve. In other words, what I'm saying is that we drop down by 40 to 0 as we get to the last piece of this beam, and that our moment, which was at 0, just extends on at 0 out to the end of the beam. So does that make sense? Yeah, it makes sense. Look, there's no load happening out in this region of the beam. There's no moment. There's no reaction moment needed to offset the load, and so this is the conclusion of this problem. And you might compare this to the part 1 problem that I posted earlier, because the only difference is that I've cantilevered the beam instead of supporting it at both ends. All right, that's it.